So for our next talk this afternoon, we're very pleased to have Martin Lesourd, and he's going to give us a snippet on mass and the topology and geometry of positive scalar curvature.
Thanks, Martin. Hello, everybody. So today I'll be talking about a small corner of, as the title suggests, the question of mass in the context of manifolds which admit an asymptotically flat end. I'll talk a little bit about topology because that plays a role. And this work is joint. It's based on 4 papers. 2 of those are based on with Ryan Unger and Professor Yao. And then 2 of those are with Dan Lee, who's with us today, and Ryan Unger. Okay, so what's the outline for this talk? I had planned to include lots of things about scalar curvature, lots of results that I find very elegant and they give a beautiful geometric and elegant description. But I had some wise interaction with Dan, who kind of slowed me down on getting too carried away with all that. So I've restricted to a subset of what I was going to do. Thanks, Dan. And we'll start with just a slide or 2 on some background, just to warm everybody up on scalar curvature, and then a small portion of the talk will be on what's the topology compatible with positive scalar curvature, which is a classical question in geometry and has been studied by a number of illustrious mathematicians. Then I will talk about the classic PMT, so positive mass theorem, because we've seen these in talks before. I won't dwell too much, but I will give you some sketches of the proofs because they're relevant for the results that I'll actually present, and the point being that I'll show you what goes wrong in the typical approaches and why you can't use them. Well, I mean, as I'll show you, you can, but you have to modify them somewhat. That will lead us into the arbitrary ends and shielding PMT, which is kind of the language we've, the labels that we've come up for the results. And then I will, rush through what I can in the last 20 minutes, half an hour, and tell you about a different proof of the shielding theorem using the density theorem for initial data sets with boundary. And that's where we'll get into the 2 latter papers that I mentioned before. And then I'll mention some natural open problems, which come up very naturally from this work. Now, again, advice of Dan told me that I shouldn't just leave my results till the end. And so I will show you the results very, very soon. But I will first give you at least a background slide, and then I'll immediately show you the results, and then we can go back to the outline of the talk, etc. So this slide is perhaps the least new to any of you. I'm sure you've seen this a dozen times, so I won't dwell too much, giving you a definition of Ricci and of the scalar curvature. And there's this nice geometric fact that if you compute the volume of small balls, then for small r, you will get that PSC will imply that the volume of small balls is smaller than their Euclidean counterparts. The fourth bullet here is sort of unremarkable, but it's useful, and there's a warped product generalization of that, which has been actually surprisingly influential. And then the fifth bullet point is actually big news. It's old news, but it's important. This was a fact that was proven first by Shen Yao, and then a more direct argument was given by Varomov-Lawson, And this is in a sense, an important reason why the condition of PSC comes up in a number of different areas and is linked, well, and can be approached from a number of different fields, from index theory to conformal geometry to geometric flows, whatever. And then this was just my one allowance of something that's completely unrelated to the talk. I promise everything else is related. This was my one allowance of a statement that's not related, but I think it's beautiful. You might ask, why am I interested in PSC? Why am I not interested in, say, R is less than C or something? Why am my inequalities always going towards the left and never towards the right? There's a philosophical reason, which is that, in fact, by theorem of Locamp, dimensions 3 and above, the subspace of metrics that have an upper bound on the scalar curvature is C0 dense in the space of all smooth metrics. So I can approach any smooth metric in C0 with metrics that have the scalar curvature bounded from above. So in a sense, scalar curvature bounds from above, but just not as interesting geometrically as bounds from below. I wish someone had showed me that before I got into scalar curvature, but I kind of very much like that fact. All right, that was my allowance for the one thing that wasn't relevant, but that hopefully warms us up. Now, another warm up, which forms really the backdrop of the whole enterprise, are the following. I mean, there are more examples I could have put here on this slide, but the basic idea is, you could say, non-negativity, right, of certain quantities, and rigidity, right? So these are some of my favorite theorems, and I shall start reading them out, and it'll be clear, obviously, which bits are about non-negativity, which bits are about rigidity. So, believe it or not, 1 and 2 of 79 are 2 different papers. I don't know what happened in that year, but it was a great year for scalar curvature. The first says that if you have a metric whose scalar curvature is non-negative on a torus, its dimensions between 3 and 7, then that actually can only happen if G is in fact Ricci flat. The second theorem, which is a different paper and is of course a landmark theorem and which forms the whole backdrop of this whole talk, is the positive mass theorem, where you have the non-negativity statement here and the rigidity statement here. So I'm not going to bore you with the statement, but very quickly, if you're asymptotically flat and the scalar curvature is non-negative, then the mass is non-negative, and 0 if and only if G is flat. Now, you can think of the next theorem as a refinement, if you like, or a theorem that applies to manifolds with a boundary, which have the geometry of being outer minimizing. So the picture is something like this. You have something asymptotically flat, and you have a minimal surface boundary, just like the time equal 0 slice of the Schwarzschild solution, and this minimal surface is outer minimizing. And in fact, in this case, you don't just prove the mass is non-negative, you prove that the mass has a lower bound given by the square root of the area over 16 pi. Those familiar with the Hawking mass will see immediately that will be the Hawking mass evaluated on this minimal sphere. And you don't just have this non-negativity, have in line with our general rigidity, and namely equality implies Schwarzschild. This next theorem of Miao is less relevant to this talk, but it's a beautiful theorem nonetheless. I'm going to pause for a second and let you read it. But essentially, it's more in this case more of a rigidity statement, which tells you about whether or not you can fill in a certain ball with a metric having the scalar curvature that's non-negative and having specific conditions on the boundary, the induced metric on the boundary, and the mean curvature. Okay, So now I promise you all the results. So everything today is here. This slide, captures everything that I'll be talking about. So I once I've gone through this slide, I could finish the talk, but you're going to have to sit with me for another 40 minutes, I'm afraid. Okay, so what are we going to do today? So the first, and perhaps, which I'll only take about maybe 5 to 10 minutes on this. The first point is, which topologies allow for scalar curvature non-negative, right? And this is a classic question. You could already see, from the Gauss-Bonnet theorem for surfaces that if the scalar curvature is everywhere positive, the Euler characteristics also positive. So you have topological obstructions, PSC. The story in higher dimensions is much more complicated and has been the subject of works ranging from, K theory, index theory, non-commutative geometry. I mean, you name it. It's been looked at by, incredible mathematicians coming at it from all kinds of different angles. And the theory and the richness of this field is just completely stunning. I mean, it goes on and on and on, and the things get harder and harder, and still people today are working very, very hard on this question. So we just look at a small corner, a paper of Shen Yao, 79, again, where they have a condition on the homology of a manifold, which obstructs it from having PSC. And what we'll do today is describe how you can generalize this to the setting where the manifold isn't necessarily closed, but it's allowed to be non-compact. I'll tell you why that's interesting. The main point being that the classic proof breaks down completely. Okay, and then the more important, sizable part of the talk is just about the positive mass theorem. So here I've said, what is the asymptotic geometry? And I've left this as an ellipse because, in fact, we'll see that we'll play around with this lower bound. So we won't just require the lower bound to be 0. We'll play around with it. Sometimes we'll make it positive. Sometimes we'll allow for it to be negative. And it's, a big part of the talk is about understanding what freedom we have in working with this lower bound. Okay, so what are the actual results and the papers? So here they are. So in dimensions 3 to 7, I'll talk about the dimensional restriction in a second, but bear with me for a minute or two. In dimensions 3 to 7, we have the positive mass with arbitrary ends. Now, arbitrary ends, I will show you what that means, but it just means that the manifold is complete and merely assumed to have one asymptotically flat end, but whose other ends could be anything. Crucially, this is not a cylindrical assumption. This is not any kind of assumption about the other ends. This is really just a complete manifold. It could be absolutely anything you like. So this yields a different proof of a conjecture of Shen Yao from a different paper, this one from 1988, where they studied the structure of locally conformally flat manifolds whose scalar curvature is non-negative. And it yields a different proof to the one that was given by 2 papers, although much of the work was in the paper of Chodosh Lee, which actually studied the problem number 1, so which topologies allow for non-negative scalar curvature. So in that same paper, the first paper, we showed that the Shen Yao conjecture, which won't be the subject of this talk, actually follows from a geometric theorem about the scalar curvature of the torus connects some with an arbitrary manifold. And this was a fact that was proven about by Chodosh and Lee in dimensions 3 to 7, and proven by us in the setting of n equals 3, and then with extra assumptions between 4 and 7. Okay, the second bit will be the density theorem for the constraint equations on an asymptotically flat initial data set with boundary. So that's a mouthful. What does density theorem mean? You'll see throughout the talk there's a kind of theme that comes up again and again. It's that when you try and prove the positive mass theorem, you have got different approaches that are available to you, and it so happens that a lot of the geometric arguments, or some of the geometric arguments you might make, end up not working out if the initial data is truly asymptotically flat in a general sense. And so there is a kind of preliminary step where you have to perturb the data in such a way that you improve the asymptotics. So throughout the talk, I'll be naming that improving the data, and the density theorem is exactly the theorem that tells you that you can do this step, whilst maintaining the right inequalities, so that in your argument for the positive mass theorem, which usually proceeds by contradiction, you're able to run your geometric arguments, which require typically a great deal of regularity or of decay. Or I should say both, really. Now, as a consequence of this density theorem for the constraint equations on an asymptotic flat with boundary, apologies for the mouthful, we prove the positive mass theorem for initial data sets with boundary in dimensions 3 to 7. So this theorem was studied as a great and rich history, and I'll describe very briefly what was known before our paper, but essentially all previous work on this theorem had either assumed something or other that we were able to do without. Of course, we still have the dimensional restriction, which will be a theme throughout the paper, but it's not actually going to be the subject of the talk at all. And finally, although I'll be very brief about this, I'll talk about another density theorem, but in this case, not for a manifold that has a boundary, but actually just for a manifold that's completely general, that could have incompleteness, that could have other ends, that could be all kinds, that could have any kind of structure. So a fun bit of history here is that when we first tried to prove the PMT with arbitrary ends, we wanted to improve the data so that our geometric arguments could work, but we didn't see that we were able to do so. And it was only in the paper we wrote with Dan and Ryan that we realized that we could actually do something. And then we revisited the original work where we had assumed asymptotic to Schwarzschild, and were able to prove the density theorem in a wider context that could close this issue, and that could resolve this issue of having to assume this extra decay. And then finally, I'll talk about some open problems, but that's not in the results section. All right, so those are the main results, and I will now actually start delving into the subject at hand. So this is a beautiful theorem. It says that closed manifolds that have the structure of a connect sum between a closed manifold X and a Schoen-Schick manifold does not admit PSC. Okay, and you'll say, okay, well, what does Schoen-Schick mean? Well, Schoen-Schick is a kind of more general version of just being a torus, essentially. What Schoen-Schick tells you is that the homology of your manifold is just so organized that you can run the Schoen-Yau inductive argument inducing on dimension. And I think it's historically relevant to note that actually, if you just have the torus, so you're not doing connect sums and you're not doing Schoen-Schick, you're just doing the torus, then the Schoen-Yau argument of 79 was generalized by Gromov-Lawson to all n using index theoretic methods. So this theorem deserves a sketch, and here it is. So let's start with the easier, having a torus connect sum with a closed manifold Xn. I do not know what Xn is, but that doesn't quite matter. And then I know that I have some non-trivial homology, say Tn minus 1, and then I can minimize in the class of Tn minus 1, and that will produce, say, a minimal torus. And this minimal torus, by deep theorems in geometric measure theory, this minimal torus will be stable. And this means that if I zoom in on this torus and I consider, say, a variation of the area, if I have a normal vector field and I vary sigma in a normal direction, then I will have the second variation of, say, the following variation of the area of sigma. So I've called my torus n-1 sigma n-1 because you'll see that in the talk we'll just talk about sigma. Then this guy is non-negative, and when this guy is non-negative, there is a beautiful argument involving the Gauss equation and so forth that tells you that in fact this means that the n-1 torus itself has to admit PSC. And that comes from looking at the conformal Laplacian, which is associated to the formula for the change in scalar curvature under a conformal change. So this is a beautiful argument. And the first part of the talk, which we'll only maybe spend another maybe 3-4 minutes on, will be that how do I want to generalize to the setting of non-compact or incomplete manifolds? So suppose I have a torus, but now rather than being connect sum with a closed manifold, it's just connect sum with an arbitrary manifold. And then you will quickly see that I still have, some non-trivial homology here. That doesn't go anywhere. But when I minimize, it could very well be that my minimizing sequence either degenerates to something non-compact, and well, it either, if I don't have any restriction on the topology, you don't even know for a non-compact manifold whether this minimizing sequence actually converges. So that's an even more, that's an even more serious issue. But in the case of a torus connect sum, you can prove that actually your minimizer has to be supported at least partly in the torus, and that means that you do get convergence, but the limit could be awful. And that's a problem because for your conformal rescaling arguments, you have no idea now if the conformal metric is complete, and so you can't run your inductive arguments. So this is a problem. Another problem that you might have is if you have, say, an incomplete manifold. So now we have an incomplete manifold, and in this case, I've just removed the point, but I could remove all kinds of things. And then we have the same problem, or a similar problem, which is that we still have this nice homology class, but of course, we could, hit that puncture, and then we don't have an embedded surface anymore that we can play around with and work our inductive argument. So these are the problems with non-compact or incomplete manifolds. And there are some results which partially quell this issue. So Cheroshli, in a very beautiful paper, proved that actually if you have SYS that's n-1 dimensional cross an S1 and you connect some with an arbitrary manifold, and that doesn't admit PSC. And we have a theorem which is trying to be of a similar spirit, which tells us that if it's SYS connects some arbitrary manifold and it doesn't admit PSC in the 3-dimensional case, that's the full result. But in dimensions 4 to 7, we have to assume this kind of nasty geometric assumption on the factor, which we didn't want to do, but it was the only way that we could close the argument. Lambda rho contractible means that lambda sized metric balls are, or rho sized metric balls are lambda Lipschitz contractible. Now, this sort of begs the question, does Schoen-Weissschick connect some arbitrary manifold admit PSC? And this is actually open. The S1 is crucially used in Cheroshli to run a mu bubbles argument. And that leads us to the next part of the talk, where we'll talk about mu bubbles. And I will spend the rest of the talk basically about mu bubbles and the positive mass theorem. But I wanted to motivate it with some topology and this kind of generalization of the Schoen-Yau arguments. Incidentally, I cannot resist mentioning another open problem in this area, which I find also rather fascinating. So let me just write it here. It wasn't in my notes, but I decided that I want to mention it. So in the very same paper of Cheroshli, and also in an argument of Misha-Gromov, there is a theorem which tells us that a closed aspherical manifold does not admit PSC in dimensions 3, 4, and 5. And aspherical means that the manifold has contractible universal cover. This was a problem that was studied a long time ago, but it was only recently solved in these dimensions, again, using mu bubbles. And what's open is aspherical connects some an arbitrary manifold. So in the dimensions where we have the theorem that applies to the aspherical factor, you might say, does this admit PSC? So far as I know, this is not known. Okay, so that's enough for the motivation and the background. And now we're going to get into the main subject, which is the PMT. So a classical theorem of Chen-Yao tells us that when you have manifolds of this kind, you take the ADM mass, which you can compute, and I'll show you the formula for that. Then this mass is non-negative when the scalar curvature of the ambient space is non-negative, and you have this rigidity. So these are kinds of manifolds you should have in mind when you think of the positive mass theorem. This is relevant for what comes next. Some general comments about the classical PMT is that, and this will hopefully give you some context for the talk and for the proofs and for what I'll be talking about, is that for n equals 3, so many great things happen, and n equals 3 is so wonderfully approachable that actually there are now a bunch of proofs of this statement. And it's really interesting to see they all have different flavors and they resemble each other, to various degrees. But the point I want to make is that for n equals 3, there are lots and lots and lots of arguments that you can use to prove the PMT, with some recent very exciting ones as well that we've seen in recent years, maybe even last year. Two really intriguing proofs that were announced last year. Now, here's the interesting thing. For general dimension, as soon as you go above n equals 3, this wealth and these riches disappear. And somehow we don't know what to do. There's only a handful of methods, or maybe 2 methods. And one involves a spin proof. And it was, the first such argument was, of course, by Witten. But the issue with the spin proof, of course, is that in dimensions 4 and above, that involves a topological assumption that the manifold is spin. And so suddenly you're not looking at the class of manifolds to which you think the PMT should hold, or for which you think the PMT should hold. So you're making an assumption which can make your proof work. That's fine, but you want to prove it more generally. And to my knowledge, the only argument that actually does that in higher dimension is, in fact, the Chen-Yao argument. And so we'll talk a lot about that. And I've written by 2 and 2 star because, in fact, the Chen-Yao argument, which I'll describe, was how it was first approached and proved. But then Locamp in 1999 came with a very clever reduction where he was able to show that if the PMT is false, so if the mass is negative, then in fact, you can put a PSC metric on a manifold of the form torus connects some xn, where xn is closed. So remember, we're back in the setting of Chen-Yao 79, and we can rule this out by the geometric theorem I told you about a few slides ago. And so another interesting thing is that these proofs, so the geometric arguments of Chen-Yao or the Locamp reduction, they involve an extra step, which is that they involve this improvement of the data, right? Which is the analytic component of the proof that I mentioned earlier, where essentially you have a general definition of asymptotic flatness, but that general definition is sort of too general for your geometric arguments to work. And so you have to improve the data, preserving the sign of the mass. And interestingly, this improvement step is really just an analytic step, and it has nothing to do with dimensional restriction. Okay, so that's some general comments. So now for the slides that I ought to show you, asymptotically flat in this talk will mean that I have the metric decaying to the flat metric in a weighted in a way the Sobolev space, where Q captures the rate of decay. And I can define the mass in this context as extra assumption that R is in L1. And this is the kind of manifold I'll be considering. And to give you a flavor of what improving the data means, well, here's an example in the simplest case, what it means to improve the data. So we say that mg is harmonically flat if g is equal to the flat metric up to a conformal factor, where the conformal factor is harmonic with respect to the Euclidean metric, and u approaches 1 at infinity. And then the density theorem, which tells you that you can perturb the data, tells you that if you have a complete asymptotically flat manifold with scalar curvature non-negative, then for any epsilon, there exists a complete harmonically flat metric such that the metric, the scalar curvature are close, but the scalar curvature is also close, and G tilde is harmonically flat. And once it's harmonically flat, you're in business, you can start proving things geometrically. So how does it work? How does the actual Shane-Yao argument work? I show you this because it's key to the proof and the sketch of the actual theorem we showed. So first of all, I'm only going to show you the non-negativity. I'm not going to show you the rigidity. Right? That's my decision. You know, we have a limited amount of time. So anyway, what you do is you improve the asymptotics using density, and I just showed you that before. And then what you do is that, having assumed that the mass is negative, you have a certain mean curvature conditions on the planes, which allow you to find a minimizer, which I've drawn as a disk here. And then you, in 3 dimensions, you study the sequence of this minimizer. You prove convergence, and then because it's a minimizer at each step, the limit inherits a stability inequality, and you prove directly that the stability inequality yields a contradiction with PSC. Now, in higher dimensions, you have to produce a counterexample to the PMT in 1 dimension below, and this is where the delicate height picking has to be done, and it almost gives you the contradiction, but the form of the contradiction is a little different. It's that you have a counterexample to the PMT in 1 dimension lower after a conformal rescaling. Okay, and then for the second approach, which works in higher dimensions, is the low camp kind of slick reduction, which tells you that if it's harmonically flat, the mass is negative and R is non-negative, then you can actually put a PSC metric on a torus connect sum, and then you can finish off the argument with an application of the classic results. So now, what is the PMT conjecture for arbitrary ends? For arbitrary ends, it's exactly in this diagram. So the other ends are just allowed to be whatever they like. And the statement is exactly analogous. So the mass is non-negative and it's equal to 0 if and only if G is in fact flat. So I should mention that in fact, a more general version of this theorem was proved using spinors by Bartnik and Kruschel in 2003. So in the case that the manifold is spin, this is well known, or at least it's been known for some time. But without this spin assumption, it's now known in dimensions 3 to 7 by combining 2 papers. So the first paper proves the theorem, the non-negativity part of the theorem, under asymptotic to Schwarzschild. The second paper with Dan and Ryan, studies the rigidity, but also proves the density theorem in the context that you so as to reach the wider class of asymptotics. Okay, so this theorem is actually a corollary of another theorem, which is called the shielding theorem, and it's shielding for very good reason. We didn't call it shielding at first, but I think I like the shielding terminology now, and I'll show you why. So here we have a manifold that has a distinguished asymptotically flat end. It's not assumed to be complete. This is key. And to have non-negative scalar curvature everywhere. But now if you have neighborhoods of this asymptotically flat end, and you have the following 3 conditions, so there's no incomplete points, at least in a D neighborhood of U1. You have the non-negative in a D neighborhood of U1, you have that the scalar curvature is not negative, and you have this largeness assumption on the scalar curvature. And this is coming back to what I promised you at the beginning of the talk, that we were going to play around with this lower bound. This is where I'm starting to play with it. So then you can show that the mass is actually strictly positive, and a theorem which was worked out a little later, a little after our first paper, using spinors was done by Cecchini and Zeidler. And you might ask, wasn't this already done by Bartnik and Crucial? But here, Cecchini and Zeidler actually allow for incompleteness, right? So that's why it's an analog of this theorem, and I wrote down Bartnik Crucial for the previous one. So at this point, I owe you a picture, because of course this is completely opaque, and here is the picture. D1, and then D0 is this distance here. Okay, so the point is that you have, remember here you have G has no, this should be D0. This has no points of incompleteness in the D0 neighborhood of U1. The scalar curvature is non-negative in the D0 neighborhood of U1, and the scalar curvature has this largeness. So that means that on this annulus, on a metric annulus, well, on a neighborhood annulus, I should say, you have that the scalar curvature obeys this largeness condition. And the point here is that everywhere outside of this diagram, so let me maybe shade it in with a different color. Everywhere here, I'm completely agnostic about. So, you know, I've nothing like a boundary with a mean curvature assumption. I have nothing like other, you know, asymptotically flat or cylindrical ends. I have nothing like that. I just have anything I want. So I could have all sorts of incompleteness. I could have, you know, terrible incompleteness of any kind. So really, actually, this whole thing is irrelevant. I don't need any of this, and all I need is this D0 neighborhood. So why does this not follow from what's known? Well, the issue with the Chen-Yao argument is the following. So here are my bad ends that could be arbitrary or could have singularities. And then remember, what we did in the proof was that we looked at these coordinate cylinders and we looked at minimizers, right? And these minimizers could explore, but then suddenly hit this incompleteness, this incomplete point. And then I have a member of my minimizing sequence which I cannot work with because it's not an embedded submanifold anymore. And then, so that's the issue with the classical Chen-Yao proof. And then the low count reduction was, remember, the mass is negative, then I can put a certain metric on a torus connect something. Well, now the analog thing, torus connect sum with a puncture, say, or with incomplete points. So that looks like this. But it's totally unclear how you go from this picture to this picture, right? Because you have to do so in such a way that preserves distances and scalar curvature. And then when you want to rule this out and say this is not allowed, you have to, all you have to play around with here are distances and lower bounds on the scalar curvature. And it's not at all clear that you can prove a theorem which rules this out. So this step is unclear, but it might be doable. But this step is certainly unclear. Okay, so if you want to ask questions at this point, or at least I could preempt some members of the audience, especially those familiar with mu bubbles, why this step is unclear, and we can talk about that at the end. But perhaps it's a question that's best left to the end. So by the way, what you would want to rule this out is a theorem that tells you can't have a metric with some lower bound on the scalar curvature and that's complete within a certain size neighborhood of your torus factor. But making that precise and proving such a thing is not clear to me. So how do you do it? How do you actually prove it? Well, it was first realized by Gromov in '96 that you can not minimize the area functional, but minimize the area minus weighted volume. And the regularity theory essentially works out in your favor and produces an embedded minimizer, but which obeys a different stability inequality. And the point is that you're going to design your volume functional so that you prohibit your candidates from ever exploring anything beyond this region, right? So they will not cross this region because here you've set h to minus infinity, and so your functional is getting very large. So your minimizers are contained, but of course, there's no such thing as a free lunch. Well, in fact, as you will see, there is a free lunch in this context, but it's kind of surprising that such a simple trick should work. Right? It seems almost, it seems so simple, but in fact, there's a kind of marvelous, computation here, which is that when you do the first variation, the mean curvature of your hypersurfaces end up being equal to h, which is a function you can freely prescribe, so long as you satisfy the third point in this slide, which is that the second variation works in your favor. Remember, the second variation was precisely the step, was precisely what you needed to compute in the Shen-Yao argument to do this inductive argument, or at least to rule something out on one dimension lower. And when you do this computation, you get the following variation, and it becomes a matter of choosing h, which satisfies this, in order to deduce that sigma admits a metric of positive scalar curvature in its conformal class. Now, you might say, okay, that's simple enough. In fact, I've cheated you here and showed you something much simpler than what you actually have to compute. Because as people who are familiar with the proofs of the PMT will go, this kind of normal variation doesn't suffice for in order to close your argument in the asymptotically flat case. But for the purposes of exposition, the point is that this is your magic condition. If you can design an H and the homology of your manifold is so organized that things that minimize your new functional are PSC averse. So for instance, they have the homology of the Tn minus 1 as it sits inside the Tn, then if you satisfy this condition, you will be able to get a contradiction. So now, yeah. Oh, I may have a typo in 4. Yeah, that's possible. Yeah, so it's like 2. Thanks. Right, so the sequence, oh, sorry. Yeah, so the sequence drawn a different way looks like this for the PMT, the shielding theorem. So the region where your PSC is working in your favor will be some annulus that sits somewhere. I'm not going to draw it because I'm going to ruin the pretty diagram. But here I have some nice lower bound on the scalar curvature. And this lower bound comes from satisfying the inequality I just showed you before on the previous slide, which had a typo. My apologies. But that's how your sequence looks. So it looks like these surfaces sigma, they have a boundary. The boundary sits on these cylinders, which is sandwiched between coordinate planes in the good end that you have. H is eventually 0 far away. So you're actually minimal asymptotically. Well, I shouldn't say asymptotically, just outside of a sphere of finite radius. And H is negative infinity to forbid your minimizers from ever trying to venture out anywhere near your boundary. Well, your boundary is not a boundary, but it's a region where H is infinite. And so the sketch of the proof is entirely analogous to the Shen-Yao proof, but with the extra complications brought about by this different variation, which I'm not going to show you because it's a rather ugly mess. But essentially, for the contradiction argument, so non-negativity proof, you assume the mass is negative, you build and control your sequence of mu bubbles, you show this sequence converges to something asymptotically flat, otherwise, you might as well not even try to prove anything. You show that this limit has 0 mass and actually admits a scalar flat metric with negative mass, but this limit is asymptotically flat and you can use the ordinary PMT. So note here that there's a slight distinction between the usual PMT proof, which tells you that you just induce in dimension. Here, you induce to something that's actually classical, that's known. So the induction isn't quite symmetric, isn't quite the same as the induction in the usual proof. You don't induce to something that's asymptotically flat with arbitrary ends. Okay, so then for the complications, well, step 2 is just more involved because there are just more terms that come from the second variation. And then there's this issue that we didn't prove density in the first effort at this. We had asymptotic to Schwarzschild, whereas harmonically flat is the really key geometric condition to make these arguments kind of one or two or three liners. When you have asymptotic to Schwarzschild, these 1 or 2 or 3 liners becomes 1 or 2 or 3 pages, and it becomes a little hairier, but it's certainly doable. And this gives you the shielding theorem, and then you can prove that the shielding theorem implies the PMT with arbitrary ends. So as a result of so this is now the 4th paper in the sequence. This you can turn the shielding theorem. You can turn the shielding theorem around, and show that actually, if the mass of your distinguished end is negative, then there is a number d which can be computed from the geometry of this asymptotically flat end, such that either the scalar curvature is negative in a d neighborhood of your end, or there is an incomplete point of your in your d neighborhood of this end. And the specific formulation was inspired by Sacchini and Zeidler, who had worked out a spinor version of the shielding theorem, which they had worked out using their own kind of generalization of Witten's proof, but that's a subject for a different day. Okay, so at this point, I have quite a lot of slides left, but I only have about 10 minutes because Marcus's question session ran over a little bit. And I now am pinned into this position of what do I cut and what do I keep? So let's see. Okay, I think for the purposes of the talk and the ideas, I'm going to skip this particular slide, which was the main result of this 3rd paper in the series. So now this paper with Dan and Ryan, where essentially this is a version of the density theorem, the original density theorem, but for the constraints with density and with a boundary. The point being that you can perturb your initial data so that you have good asymptotics on the end, you still preserve all the key inequalities, and you can prescribe your new expansion, so trace chi for the hyperbolic among you, to be to be some small delta. To be smaller than some delta. So I'm going to skip this. The point is that it generalizes the vacuum density theorem of Corvino-Shane 2005. And it is, in a sense, just a boundary analog of the density theorem that appears in the space-time positive mass theorem in the usual asymptotically flat case that was done by Aichmeier, Huang, Li, Shane in dimensions 3 to 7. So I skipped this, forgive me, but because I wanted to show you this, which is the other result in that very same paper, which is now a kind of as good as you want it to be statement of the positive mass theorem in dimensions 3 to 7 for initial data sets satisfying dominant energy condition with weak inequalities on the boundary. And in this case, we have kind of all three components. So the first component says that E is bigger than P. I'm not going to bore you with the definitions. You've seen them in talks before. Then the second bit is kind of a rigidity, which tells you if E equals P, then E equals P equals 0. And then the final part is if E equals 0, then MG isometrically embeds in Minkowski spacetime. And there is no boundary. So this theorem is a kind of combination of the density theorem we prove and lots of other theorems that have been done by lots of other authors. And I can't give a full literature review, but here are the basic, some of the basic references, which include in parentheses the kind of main tools or ideas that were used to prove. But the point is that all of these contributions are either in the case of no boundary, or they're in the case of n equals 3, which remember is the case in which we can do all kinds of things. And then they're in, or they assume a spin assumption. And I should mention that they also, so in this theorem, you have three parts. You have the inequality, the rigidity, and the embedding. I should mention that in these papers, you don't always have the three parts. You have some part, not the other part, not the other. They all study different things. But in all fairness, the pieces 2 and 3 are in a sense, and even 1 are in a sense reductions to the arguments in these papers by using the density theorem. So you should really see this theorem as just a corollary of the density theorem and the work of other authors. That's what I'm trying to say here. In particular, Aichmeier, Huang, Li, Shane, which is kind of the initial data set generalization of the Shane argument using MOTS, using Aichmeier's MOTS existence result. Okay. And so I have 7 minutes left, but I definitely want to leave time for questions. So let me finish with a cute observation, which is that these mu bubbles are in a sense prescribed mean curvature surfaces. You choose an H to make your functional behave well and get rid of the portions and parts of your manifold you don't want to deal with because they're incomplete or arbitrary or non-compact or whatever. And it turns out that in fact this is very closely related to MOTS. MOTS being the surfaces you all know and love and you've seen many times before, so I don't need to explain to you what those are. But the point is that if you define, and we've seen this before, we saw this in Greg's talk, in Dimitri's talk, if you just artificially set your second fundamental form in your initial data to be related to your metric in the following way, where now you have H here appearing, then what you can show is that in fact sigma is a stable mu bubble if and only if sigma is a stable MOTS with respect to this artificial initial data. So there's this bridge where you can use results about initial data sets to prove theorems about Riemannian geometry, where the setting in which you're doing your Riemannian geometry is different from the usual setting. It's somehow more complicated, more difficult, whatever. But you use your space-time results and then an artificial construction to get you home and dry. Okay, so how do we use the theorem I just showed you, the one that is the space-time positive mass theorem with boundary from dimensions 3 to 7, which in a sense, culminates the density and all this other work by all these people that I've been mentioning. Well, you can construct an H, and then instead of using the mu bubble argument, which had to study directly all the inequalities, etc., you can just design your H so that you can apply the space-time positive mass theorem that I just showed you, but now that has a boundary where this boundary acts as a barrier and replaces, in a sense, the h equals minus infinity barrier that you constructed when you were doing your mu bubble argument. And this gives you the shielding theorem that I showed you in the Riemannian context, but with general asymptotics. And I should mention that there's a different proof to this also in our fourth paper, which just does the Riemannian version of the density theorem, but a density theorem that now allows for all the kinds of bad things that you might have. Whereas here I'm really using the space-time positive mass theorem and the density theorem that there's an analogous density theorem, but for initial data sets. So in a sense, much more complicated, that occurs in that paper. And one thing that's nice, and just to finish off here, is that typically when you prove a PMT with a boundary, for a manifold with a boundary, you have to assume that the mean curvature has a sign. In particular, that it's either weakly outer trapped, or in the context of Riemannian geometry, that moving out of the manifold, so away from the asymptotically flat end, your area is increasing. In other words, the mean curvature measured is positive in the direction out of your manifold. Well, here, what's interesting is that you can actually prove a PMT, but where the mean curvature has exactly the opposite sign, but you compensate that with extra positivity of the scalar curvature. So I think the point here, if there's any lesson that we learn from this, is that whenever you have bad things in your manifolds that would normally thwart any attempt at proving or trying to prove the statement using the typical methods, you can compensate that by having strict lower bounds on the PSC, which somehow make the proof work, which somehow gets you to the finish line, even though a priori you had a statement for which the usual methods would manifestly powerless to prove the theorem you wanted. Finally, in just the last minute or two, the open problem. So the open problem is just the same positive mass theorem, but now for initial data sets with arbitrary ends. So that's not known. In dimensions 3, I believe you could do things, but in high dimensions, all the other proofs that we have don't work anyway. Well, at least not for now. If someone has a general proof for the PMT, of course, that is different from the proofs I've shown, maybe it can also prove this. But I should also mention that this paper of Bartley Crucial actually does prove this, or at least part of this, under a spin assumption, where again you can use your spinners to your advantage. So that's open problem number 1. But the shielding analog of that is open problem number 2, would be a kind of DEC, dominant energy scalar, that we heard about in Lance's talk, where if the DEC is strict on a kind of similar, I put A here because I don't know what the constant should be, but if the DEC is somehow strictly supported on this kind of neighborhood annulus, then perhaps you can prove a shielding version of the DEC theorem. And again, I think in dimensions 3, this might be doable with current methods. I don't know how to do it, but I think it might be around the corner. But certainly in high dimensions, I've absolutely no idea. Well, at least, I mean, it's not at all clear. I think you'd have to do a lot of work and reinvent a lot of the tools that we used. It's certainly an interesting problem. And I think it would be, it would give the exact analog of what was done in the Riemannian setting. Okay, but I've talked, for a long time now, so I should end here.
Thank you, Martin, for the nice talk. Are there any questions? Oh, that's a different thing. Sorry.
Hi, Bern. Very nice talk. So So, okay, so you're using these mu bubbles to leverage large energy density in a large region. I was just wondering, can you prove some kind of hoop conjecture sort of results using these ideas? It seems similar, or do you disagree? And are these ideas not so similar? What do you think about that question?
Well, certainly. Okay, so I think, first of all, I think that's a great question, and I want to talk about this for a long time, but I can't because, you know, time is upon us. But basically, I mean, you've identified something. So, okay, I don't need to tell you, Dimitri, or people, you've seen those papers, but of course, as you know, the Shenyao 83 paper, right, which has this, you know, kind of hoop conjecture type statement, well, it's not a hoop conjecture, but it's certainly a Mott's existence statement, relies on studying the, you know, a certain radius that's defined on a certain domain that satisfies a certain Dirichlet bound. And it turns out that the very same distance estimate is proven with mu bubbles in the Chodoshli paper. So you certainly preempted the right thing. And so certainly I think that something can be done. For the DEC shielding type hoop conjecture, I would be less convinced. So I think what you can prove is probably existence of minimal surfaces using, existence of Motts. You can probably prove such a thing using, you know, Jang arguments and then mu bubbles in the Jang graph. You can probably do such a thing. Yeah, I believe that. Now, the case of quasi-local mass was something that was very close to my heart. I worked on this with Agil and Yao, and we have a kind of effort in trying to do a kind of version of the Xi-Tam argument that was done in 2007, but using the Wang-Yao mass or Li-Yao mass. I don't see mu bubbles being useful there, but I think there is something that we haven't found yet, which is a kind of space-time version of mu bubbles. And I think that's going to be the real gold mine. Once somebody figures that out, I think that then you will be able to prove all kinds of nice theorems for DEC scalar regions. So kind of you know, something that acts and plays and smells like mu bubbles, but that actually lives in space-time. That I think has a lot of potential. There's something in the chat. Oh, there is a hand, yeah. Yes, Lon.
So thank you for a very interesting talk. So my question is like, so you already proved in the Riemannian case, the positive mass theorem holds if you have other ends which are really arbitrary. And now you present space-time PNT with the boundary, right? So it looks like probably the boundary condition seems to be less relevant, right? It's more like suppose you have a boundary, and then if you can extend that to some end, complete manifold. And if you have a version of the theorem for like a PNT with arbitrary ends with corner, right, like the Miao's type of work, and then once you have the extension of the boundary, is somehow the exact geometry, whether it's mods or not, or inner outer mods, probably not relevant, right? You just need to have extension to an end, and then you can conclude your asymptotic flat end has a non-negative mass. Is that my understanding correct?
So which setting are you talking about? The initial data or Riemannian?
Right, so I'm thinking about, let's say Riemannian case, just for, because now we already proved the theorem with arbitrary ends, yeah. Right? So it looks like the previous result for the Riemannian positive mass theorem with ends need to assume some condition on mean curvature minimum, or like I forgot the sign.
Right, yeah.
Right. And now you just can't do extensions. You just need some boundary condition. You can extend the manifold to the other side where it was not defined originally to make it complete. And yes, then the extension probably has corner, right? So now you just need a version of positive mass theorem with corner. So,
so that's yeah. I mean, so that's actually forthcoming. So I'm working right now on a corner version of this. So I mean, I have the corner theorem. We have it, with Dan and Ryan. So I think, yes, I mean, there is a corner version of these arguments. Does that answer you? I mean, yeah, you kind of stole my thunder here, but
Right. So then the consequence of your upcoming work will be you can really looking at the boundary, which essentially probably no condition, right? Of course, you have to rule out like the negative mass threshold as long as you have extension. So the extension could be even easier because
but you need some like
don't need to asymptotic flat, right? You just need extension with non-negative scalar curvature.
Yeah, but you need to show that the boundaries you have can be extended in such a way that you have non-negative.
Right, I think it's more well known. There's a bigger class of boundary geometry, for example, by the work of Xi and Tan, and there's a recent work of Xi and Yuguang Shi, and I think probably his students. They have done a lot of things which you have a bionic boundary data with induced matrix and mean curvature, and then they can do extension, right? Do I understand that? So there's a large class of boundary data you can do extension.
Yeah, absolutely. Absolutely. I mean, what you can show, in fact, is, I mean, we should really just talk about this together, because I can tell you about some of the results that we have, which generalize these results of Xi and his students in the non-compact setting. So maybe we should just talk that, but maybe this is not the place to have that conversation.
Yeah, sure. Yeah, you'll be too long.
Yeah, I wouldn't want to keep people.
Okay, are there any more questions? If not, we should thank Martin again, but I think now is also a good time to thank him for the incredible amount of work